In this lecture, I will explain the energy fluctuations in canonical ensemble. So, what is the need of studying this energy fluctuation in canonical ensemble? For that, I will first explain the difference of approach between microcanonical ensemble and canonical ensemble. In the case of microcanonical ensemble, we have a macro state which is defined by a fixed energy E and a fixed number of particle N, fixed volume V. But practically, it is not possible to fix at a particular value of energy. Any practical system, the energy will have some fluctuation, and we can say that the energy will vary between E minus delta by 2 to E plus delta by 2. That is practically a microcanonical ensemble is a system whose energy is restricted to a very narrow range. And in the case of canonical ensemble, energy can take any value between 0 and infinity. Here, the macro state is defined by a fixed number of particles, a fixed volume, and a fixed temperature. Instead of fixing the energy, here in the case of canonical ensemble, we fixed the temperature of the system. Here energy is a variable. E can take any value from 0 to infinity. Okay. And in the previous lectures, we discussed these two ensembles and we solved the classical ideal gas. We solved classical ideal gas. We derived all the thermodynamics of the system using these two approaches. And we got identical results. We got identical results for all thermodynamic properties of the system. Okay, we have derived all the thermodynamic properties using microcanonical ensemble approach as well as canonical ensemble approach for the classical ideal gas. Now, what is the reason for this equivalence? We already seen that this microcanonical ensemble energy is restricted to a very narrow range. For canonical ensemble, it can take any value between 0 and infinity. Then, why these two approaches give identical results? What is the reason for this equivalence? For finding that reason, we are going to study the energy fluctuations in canonical ensemble. We will calculate the actual extent of energy over which the system energy can spread with a significant probability. സിസ്റ്റത്തിന്റെ എനർജിക്ക് ഏത് റേഞ്ചിൽ വരെ സ്പ്രെഡ് ചെയ്യാം ഒരു സിഗ്നിഫിക്കന്റ് പ്രോബബിലിറ്റിയോടുകൂടി ദാറ്റ് വി വിൽ ഫൈൻഡ് ദാറ്റ് വി വിൽ കാൽക്കുലേറ്റ് ആൻഡ് ദാറ്റ് കാൽക്കുലേഷൻ വിൽ ഗീവ് ദ ആൻസർ ഫോർ ദിസ് ക്വസ്റ്റ്യൻ. Now, the extent up to which this energy can spread gives you a measure of the extent up to which canonical ensemble really differs from microcanonical ensemble. If the spread of energy is very large, then the deviation of canonical ensemble results compared to microcanonical ensemble will be large. So that spread will give you the extent up to which canonical ensemble really differs from microcanonical ensemble. So that is our idea. Now we have for mean energy or the expectation value of energy, the equation is sigma r er e raised to minus beta er divided by sigma r e raised to minus beta er. Here e raised to minus beta er is known as Boltzmann factor, and e raised to minus beta er divided by sigma r e raised to minus beta er is called probability of finding the system in an energy eigenvalue er. In an energy eigenvalue er. So, summation energy multiplied with the probability will give you the average value of energy. Will give you the average value of energy. Average value of any quantity in a canonical ensemble, I can write it as sigma r xr pr, where pr is the probability of finding the system in a value of xr, and there are various microstates. Sum over all the microstates, you will get the average value of that quantity. So for here energy, and what is the value of PR? PR is actually e raised to minus beta ER divided by sigma R e raised to minus beta ER. So for any quantity, you can find its average value using this expression. So average value of energy is given by sigma R ER PR. So this is the value of PR. So mean energy is given by this equation 1. We will differentiate that equation with respect to beta. So dou u by dou beta. We will keep this energy eigenvalue constant. Keeping ER constant, we are going to take the derivative with respect to beta. You can take denominator as one function and numerator as the other function. Okay. So I will keep 1 divided by sigma r e raised to minus beta er as constant, and I will take the derivative of numerator. That will give me sigma r er e raised to minus beta er multiplied with minus er, because e raised to minus beta er derivative is e raised to minus beta er multiplied with minus er, because we are taking derivative with respect to beta. Now numerator into sigma r e raised to minus beta er is the numerator, into derivative of 1 divided by this quantity. Derivative of 1 by x is minus 1 by x square. So derivative of 1 by this quantity is minus 1 divided by that quantity square. Okay, minus 1 divided by sigma r e raised to minus beta er square. But the derivative is with respect to beta, so you have to take the derivative of this function. That will be sigma r e raised to minus beta er. Again, function of a function, derivative should be with respect to beta. So take the derivative of minus beta er. That will give you a minus er. Now rearranging. Here you have a negative sign. I put it here. ER multiplied with ER will give you ER square. So this is sigma R ER square e raised to minus beta ER divided by sigma R e raised to minus beta ER plus sigma R ER e raised to minus beta ER whole square. Because here you have a sigma R ER e raised to minus beta ER. Here you have a sigma R ER e raised to minus beta ER. This minus and this minus becomes plus. Denominator is already a square quantity. So this can be written as whole square. Now what is this? I already mentioned, if you have any quantity xr multiplied with the probability and sum over all states, that will give you average value of that quantity. So here ER square multiplied with the probability and sum over all states will give you the average value of E square. This is average value of E the whole square. Average value of E the whole square. So dou u by dou beta is minus average of E square plus average E whole square. But fluctuation in energy delta E can be written as E minus mean value of energy. And the square fluctuation delta E square is E square minus 2E into mean value of E plus mean value square, because this is A minus B the whole square. A square minus 2AB plus B square. Now mean square fluctuation. Okay. So this is mean value of E square minus 2 times mean value of E. Here it is a mean value. If you take one more mean, that doesn't give you anything new, that it is same as mean value of E plus mean value of mean value E square. That is again mean value E square. So mean square fluctuation, I can write it as mean value of E square minus 2 times mean value E square plus mean value E square. That is minus 2 plus 1. You will get minus mean value E square. Call this as equation number 3. From 2 and 3, this is say equation number 2. This is equation number 3. from 2 and 3, you can write dou u by dou beta as minus of mean square fluctuation. Mean square fluctuation. Okay. Compare this equation 2 and 3. Then you will get it as minus of mean square fluctuation. So mean square fluctuation is minus dou u by dou beta, but beta is 1 by kt, and you can take the derivative here. You can take 1 by k outside, and derivative of 1 by t is minus 1 by t square dt. So you can write this as minus dou u by minus 1 by kt square dou t. Okay, this minus 1 by kt square go to the numerator, that becomes kt square dou u by dou t. Kt square dou u by dou t. So mean square fluctuation is kt square into dou u by dou t at constant n and v. How I wrote this constant n and v? Because we started with the derivative of u with respect to beta, keeping the energy eigenvalue constant. Keeping energy eigenvalue constant means that we are keeping number of particles and volume constant, because energy eigenvalue depends on number of particles of the system and volume of the system. So keeping ER constant means that keeping N and V constant. What is dou U by dou T at a constant N and V? It is specific heat at a constant volume. Specific heat at a constant volume, CV. So root means square fluctuation. Root means square fluctuation. Take a square root of this. Root mean square fluctuation is nothing but square root of kt square cv. If you take the relative root mean square fluctuation, that is root mean square fluctuation divided by the mean value of energy, that is known as relative root mean square fluctuation, that is equal to square root of kt square cv divided by u. That means the relative RMS fluctuation is proportional to square root CV divided by U, because K is a constant, T is a constant for canonical ensemble. So square root CV by U. CV is specific heat capacity. It is an extensive quantity. That means it is directly proportional to size of the system, or we can say that CV is proportional to number of particles in the system. So it is square root n divided by U, the average energy of the system, that is also proportional to n. So I can say that this is root n by n. This varies as relative RMS fluctuation varies as root n divided by n, and that is nothing but 1 by root n. 1 by root n. Okay. If n is very large, we can say that the RMS fluctuation in the values of energy E is negligible, because the relative RMS fluctuation is proportional to 1 by square root n. If n is very large, that is true for any statistical system, the number of particles will be of the order of 10 to the power 23 per centimeter cube or so. So for that high value of n, the RMS fluctuation, relative RMS fluctuation, the value of energy E is negligible. So for all practical purposes, a system in canonical ensemble has an energy equal to or almost equal to mean energy U. Okay. Relative RMS fluctuation around the mean value is very small. So even though the energy can vary from 0 to infinity, system will be most of the time in an energy range which is very small. The RMS fluctuation in energy is very small. Okay. We have the case of microcanonical ensemble like this. Energy cannot be strictly a constant. So there will be a small fluctuation in energy. So energy can vary from E minus delta by 2 to E plus delta by 2. That is the case with microcanonical. Microcanonical. Okay, you can represent it like this. For canonical also, even though the energy can vary from 0 to infinity, theoretically, practically the system will be in an energy range around the mean value. or around the mean value, the relative RMS fluctuation, relative root mean square fluctuation is of the order of 1 by root n. For statistical systems, this n is very large. That means relative RMS fluctuation will be very small. That is why the treatment of microcanonical ensemble and canonical ensemble gives us identical results. Okay. Now we will consider the way in which energy is distributed among the various members of the canonical ensemble. Okay. In a canonical ensemble, we have a large number of identical systems, and an energy is distributed among the member systems. The member systems can take any value of energy, and there is exchange of energy between these member systems. So now we will consider the way in which energy is distributed among the various members of the ensemble. Let E is a continuous variable. Okay, energy is a continuous variable. Then probability of finding a system in the ensemble in an energy range E to E plus dE is given by P of E dE proportional to e raised to minus beta E into G of E dE. That is, probability density is product of two terms. Probability density is product of two terms. One is Boltzmann factor, that is e raised to minus beta E. It monotonically decreases with energy. As energy increases, it will decrease continuously. Okay. Second factor is this density of states. Density of states, usually the dependence will be such that it monotonically increases with energy. It will monotonically increases with energy. So there are two factors, and probability density is the product of these two factors. One factor will monotonically decrease with energy. The other factor will monotonically increase with energy. So naturally, we can expect an extremum. We can expect an extremum at some value of E. Say E star. Okay. And at this extremum point, the first derivative of the probability density will vanish. That is, we can write dou by dou E of P of E evaluated at E equal to E star is 0. Evaluated at E equal to E star is 0. And substitute for P of E, it is product of E raised to minus beta E Boltzmann factor into density of states G of E. And you take the derivative, apply product rule. First you keep G of E as constant. Derivative of E raised to minus beta E is E raised to minus beta E multiplied with the minus beta, because here we are taking derivative with respect to E, plus first function e raised to minus beta E into derivative of second dou G by dou E evaluated at E equal to E star, that is equal to 0. And this will be true only if dou G by dou E evaluated at E equal to E star equal to beta G of E evaluated at E equal to E star. Then these two terms will cancel. So we can write it as, you can take this G to the left hand side, so that becomes 1 by G of E dou G by dou E evaluated at E equal to E star equal to beta. I can write this as dou by dou E of log G, because derivative of log x is 1 by x. So derivative of log G of E is 1 by G into dou by dou E of G. That is this thing. So I can write this as dou by dou E of log G evaluated at E equal to E star equal to beta. Call this as equation 5. But we have from microcanonical ensemble, if a system is at an energy E, entropy is given by S equal to K log omega, where omega is the number of microstates at this energy value E. Also, dou S by dou E, partial derivative of entropy with respect to E at the average value of E is equal to 1 by T. These are the results from microcanonical ensemble. And here the number of states having energy E is G of E. In the case of canonical ensemble, we know that G of E is the density of states or the number of states having an energy E. So instead of omega, you can substitute G. So S is equal to K log G. Because omega is the number of microstates having energy E. Here, in the case of canonical ensemble, we can have different energy values and we took G of E as the number of states having energy E. So we can substitute instead of omega, we can substitute G. So it is S equal to K log G. I can write the second expression dou S by dou E as dou by dou E of K log G at E equal to U equal to 1 by T. Or you can take this K to this side, okay, then it will be dou by dou E of log G evaluated at E equal to U equal to beta, because this K will go to this side, then it becomes 1 by KT. 1 by KT is beta. Comparing 5 and 6, both has RHS beta and the LHS dou by dou E. Here also dou by dou E. This is log G, this is log G. The only difference is here it is evaluated at E equal to E star, here it is E equal to U. So comparing 5 and 6, we can say that the most probable value of energy, that is E star, most probable value of energy, that is E star, is equal to mean value of energy. Most probable value of energy is equal to mean value of energy. Now we will expand log P of E around E equal to either the most probable value or the mean value. Both are equal. Both are equal. So we can expand log P of P, which is a function of E, around the energy value E star, which is approximately U. So log e raised to minus beta e g of e, that is the value of P of E, is equal to log e raised to minus beta u g of u. Because Taylor expansion, the first term is the value of function evaluated at that particular point. If you expand f of x as a Taylor expansion, f of x, the Taylor expansion around x equal to x naught is f of x naught plus x minus x naught by 1 factorial f prime x naught, where f prime x naught is the first derivative of the function evaluated at x equal to x naught. Then the second term is x minus x naught square divided by 2 factorial f double prime x naught plus etc. So here we can write it as logarithm of e raised to minus beta e g of p. The Taylor expansion is logarithm of e raised to minus beta u g of p. Instead of this f of x naught, we will have something like this plus e minus u by 1 factorial into first derivative dou by dou e of log e raised to minus beta e g of e evaluated at e equal to u plus e minus u the whole square by 2 factorial. That 2 factorial is simply 2. The second derivative dou square by dou e square of the function at e equal to u and so on. Okay, plus etc. This first term log e raised to minus beta u is simply minus beta u, because log and exponential are complementary. If you cancel, that will give you minus beta u. Log g of u, log g is nothing but s by k, because s is equal to k log g. So log g is s by k. So that gives the first term. Plus here the derivative is logarithm. Derivative is 1 divided by e raised to minus beta e into g of e. Okay, this g of e is not on the power. This is into multiplied g of e into dou by dou e of this quantity, function of a function, property which dou by dou e of this function evaluated at e equal to u into e minus u plus 1 by 2 into e minus u whole square dou square by dou e square. Logarithm of e raised to minus beta e is minus beta e plus log g. Okay, log g. Now this I can write it as logarithm of, that is the left hand side, logarithm of e raised to minus beta e g of e equal to minus beta u minus t as the first term plus 0. Why plus 0? Because you know that dou by dou e raised to minus beta e g of e evaluated at e equal to e star is 0. And e star and u are the same. So this quantity evaluated at e equal to u will also be 0. So here in the first derivative term, you have a quantity dou by dou e raised to minus beta e g of e evaluated at e equal to u. That will be 0. Then the last term plus half into e minus u the whole square into dou square by dou e square of minus beta e plus dou square by dou e square of log g evaluated at e equal to u. What is the second derivative of minus beta e? First derivative it will give you minus beta. One more derivative that will give you 0. Here you can write it as dou by dou e of dou by dou e log g. Two derivatives. What is log g? S by k. S by k. Okay, all these terms are same. Only the change is in the last term. Log g is s by k. Substitute here. K will come outside, so this becomes 1 by 2k e minus u the whole square dou by dou e of dou s by dou e. What is dou s by dou e? What is dou s by dou e? It is 1 by t, because we already know dou s by dou e is 1 by t. So I will put here as 1 by t. What is the derivative of 1 by t? It is minus 1 by t square. So this plus becomes minus 1 by t square into dou t by dou e. What is dou t by dou e? Dou e by dou t at e equal to u is Cv. So dou t by dou e at e equal to u is 1 by Cv. Okay, because we have the definition of Cv as, is it, is it, this is dou u by dou t. That is dou e by dou t at e equal to u. That is Cv. Specific capacity constant volume. So here you can substitute this as 1 by Cv. So rearranging, I can write log e raised to minus beta e g of e equal to minus beta into u minus ts minus e minus u the whole square divided by 2k t square cv. Here you have 2k t square cv in the denominator. So what is probability density P of E? It is proportional to e raised to minus beta E g of E. So you have to take exponential of this time in order to cancel this logarithm. So take exponential e raised to minus beta u minus ts into e raised to minus e minus u the whole square by 2k t square cv. This is actually a Gaussian distribution. If you plot this, you will get a Gaussian distribution in energy with the mean value u and dispersion square root of k t square cv, because this is the standard form of a Gaussian. N function of x mu comma sigma is defined as 1 by root 2 pi sigma square e raised to minus half into x minus mu whole square divided by sigma square. This is the standard definition of Gaussian, which is a peak centered at x equal to mu, and has a dispersion, or you can call it as standard deviation as sigma. So instead of sigma, here you have square root kt square cv. Square root kt square cv. This is sigma square. So this should be square root of sigma should be square root of kt square cv. Okay. So now you can use a reduced variable also. You can take a u outside from here. Okay, take a u outside. Then this becomes e by u minus 1 the whole square. When you take u outside, that will be u square, because you are taking u from a square quantity. Outside it will be u square, that you can go to that denominator. So this will be something like e raised to minus e by u minus 1 the whole square divided by 2k t square cv by u square. So if you compare this with your definition of Gaussian distribution, you can say that this Gaussian is centered around 1. Okay, if you plot it using a reduced variable E by U, this is centered around 1 and with a dispersion square root of kt square Cv by U square. Square root of kt square Cv by U square. You can take U square outside of the square root, then it will be U. So dispersion is square root kt square Cv by U. This dispersion is also known as standard deviation. Here the mean value is 1. Okay, this graph will be centered around 1. So we can say that dispersion is proportional to CV. CV is an extensive quantity. It is proportional to n. So it is square root n in the numerator. Average energy U is also an extensive quantity. So it is also proportional to n. So it is root n divided by n, and that I can write it as 1 by root n. So what is the meaning of this? If n is very much greater than 1, and that is the case with most of the statistical system, dispersion will be very small. Dispersion will be very small means this width is very small. So you will get a sharply peaked function. You will get an extremely sharp distribution. And in the limit n tends to infinity, if n tends to infinity, then it becomes a Dirac delta function. Then it becomes a Dirac delta function. Now we will consider the example of classical ideal gas. For a classical ideal gas, the density of states G of E is proportional to E raised to 3n by 2 minus 1. This we calculated in the last lecture. Using partition function, and we can see that G of E is a rapidly increasing function. As n increases, it increases very rapidly. Okay, e raised to 3n by 2 minus 1 is a very rapidly increasing function with respect to E, and e raised to minus beta e, which is a very rapidly decreasing function. It is an exponentially decaying function. So one is an increasing function, the other one is a decreasing function. What about the product? G of e into e raised to minus beta e. It is e raised to 3n by 2 minus 1 into e raised to minus beta e. This product will have a maximum at E star. Here the extremum will be a maximum, and that occurs at E star. And we can say that the first derivative of this product evaluated at E equal to E star will be 0. Because for an extremum, or here it is a maximum, for a maximum the first derivative will vanish. So take derivative e raised to minus beta e. Derivative is e raised to minus beta e into minus beta into second function e raised to 3n by 2 minus 1 plus e raised to minus beta e, keep it as a constant, and from the first two times you take it as outside. E raised to 3n by 2 minus 1, derivative is 3n by 2 minus 1 e raised to 3n by 2 minus 2, because x raised to n, derivative is n x raised to n minus 1. This quantity evaluated at E equal to E star is 0. That is, you can say that you can take this e raised to 3n by 2 minus 1 also outside. Then the first time only contains minus beta, plus second time contains 3n by 2 minus 1 divided by e. Because this is e raised to 3n by 2 minus 2, we will take outside and e raised to 3n by 2 minus 1. So here there will be a 1 by e. So that is minus beta plus 3n by 2 minus 1 into 1 by e. Evaluated at e equal to e star is 0. So e star, you will obtain it as, just to rearrange this, 3n by 2 minus 1 into beta raised to minus 1. Okay. Take this minus beta into the other side and you write an expression for e, and that is at e star. That is at the value of e star. So you will get it as e star equal to 3n by 2 minus 1 beta inverse. We already have an expression for average energy of a system. It is U equal to 3 by 2 n kT. And kT is nothing but beta raised to minus 1. So it is 3n by 2 beta raised to minus 1. So u is 3n by 2 beta raised to minus 1. E star is 3n by 2 minus 1 beta raised to minus 1. Both these will be identical in the limit n tends to infinity. When n is very large, 3n by 2 minus 1 is approximately 3n by 2. So these two are equal. So E star is approximately u when n is very large. Suppose I take n as 10. Okay, a very simple example. Take n is equal to 10. Then what is E star? From this expression, 3 into 10, 30 by 2, 15 minus 1, 14. 14 beta inverse. What is u? It is 3 into 10, 30 by 2, 15 beta inverse. 15 beta inverse. So what is the relation between E star and u? E star is equal to 14 by 15 u. 14 by 15 u. In this case, your curve, what is which curve? Curve of g of e into e raised to minus beta e will not be symmetric with respect to e star. That I will explain soon. It will not be symmetric with respect to e star. We can calculate the width of the curve also, the dispersion or standard deviation. We already defined it as delta is equal to square root kt square cv. Okay, square root kt square cv. Here we have the expression for dispersion as square root kt square cv. It is a measure of the width of this curve. So that I will calculate square root kt square Cv. Cv is nothing but 3 by 2 Nk, 3 by 2 Nk, specific heat at a constant volume for monoatomic molecule. And this K and this K becomes K square. K square T square is 1 by beta square. So 3n by 2, 1 by beta square. It is square root 3n by 2, 1 by beta square. I can write it as simply again Kt. So this is delta. You can multiply and divide it with a u. Multiply with u and divide with u. Then replace u with the 3 by 2 and kt. Kt will cancel. Root 3n by 2 in the numerator, 3n by 2 in the denominator. That will give you a root 3n by 2 in the denominator. And there is a u. So that becomes delta is square root 2 by 3n u. Delta, the width of the graph is square root 2 by 3 n u. For n equal to 10, for n equal to 10, that delta will be, if you put n equal to 10, this will be 2 by 30. 2 by 30 is 1 by 15. 1 by 15 root is roughly 1 by 4. So it is, the width is 1 by 4th of the mean energy value. 1 by 4th of the mean energy value. Okay. Now, as n increases, what will happen to u and e star? As n increases, this value will increase, this value will increase. And this ratio, 14 by 15 becomes, say, 100 by 101, and then it becomes 1000 by 1001. So these two numbers are differ by just a 1. So if the number increases, this will approaches a value of unity. And you can say that E star is approximately U. Okay. If you increase the value of n, both numerator and denominator increases, they will always differ by 1. That is, if the numerator is 99, denominator will be 100. The numerator is 999, denominator will be 1000. Okay. So as the value of n increases, E star approaches U, or E star by U approaches unity. E star by U approaches unity. What about delta? Delta increases as, what is the equation for delta? Delta is 1 by root n, right? 1 by root n. Here there is a u. U depends on, or u is directly proportional to n. So in effect delta is proportional to root n. Delta is proportional to root n, or delta increases as n raised to half. But delta by u, the relative fluctuation, delta is the width divided by the mean value, will decreases as n raised to minus half. N raised to minus half. This is n raised to half. If you divide it with the u, u has an independence n raised to 1. So that will give you n raised to minus half. That means the relative width tends to vanish as n tends to infinity. Because this is 1 by root n, as n tends to infinity, the relative width of the graph tends to vanish. Now, I will explain this graph which is shown in Pathria's textbook. Here there are two curves. One is g of e, that is an exponentially, not exponentially, it is e raised to 3n by 2 minus 1. It is an increasing function, rapidly increasing function. Then there is e raised to minus beta e, that is an exponentially decreasing function. And the product is something like this. And you can clearly see that this is not symmetrical. This graph is not symmetrical around the value e star. Okay, this peak is E star and the value at which these two meets, that is U. Okay, that is the difference. This peak is E star and this curve is not symmetric around E star. Okay. Also, there is one more thing. The numerical values of the functions. Here the values are not actually g of e. The numerical value of these graphs are actually g of e divided by g of u. That is specified here. The numerical values of the functions have been expressed as fractions of their respective values at e equal to u. That means at this point the value is not g of e but g of e divided by g of u. And in this graph the value right here is not e raised to minus beta e but it is e raised to minus beta e divided by e raised to minus beta u. Okay, so the values of the functions have been expressed as fractions of their respective values at equal to u. I will explain all this. So look at this figure. Consider a case with the n equal to 10. Your g of e, density of states, is e raised to 3n by 2 minus 1. So g of e divided by g of u will be e divided by u raised to 3n by 2 minus 1. 3n by 2 minus 1. What is n here? It is n. So 3n by 2 is 15 minus 1 is 14. So g of e divided by g of u is e by u raised to 14. E by u raised to 14 is like this. Okay, this is the actual plot of e by u raised to 14. In this axis, it is e by u. When e by u is 1, that becomes 1 raised to 14 and it is 1. Okay, this on this x-axis, it is e by u. When e by u is equal to 1, your graph, the value will be 1. And then as e by u increases, it rapidly increases. Now consider this graph, this exponentially decaying graph. It is again for n equal to 10. We are representing on this graph the value of e raised to minus beta e divided by e raised to minus beta u. Then it is e raised to minus beta into e minus u. You can take this u outside, then it becomes e raised to minus beta u into e by u minus 1. What is beta u? Beta u is 15 because here you can see that beta, this is 1, beta inverse is 1 by beta. Beta u is 15 when n is equal to 10. So in this graph, it is e raised to minus 15 into e by u minus 1. So again, on the x-axis, we are representing e by u. So when e by u equal to 1, e by u equal to 1, this becomes e raised to 0. E raised to 0 is 1. Okay. As e by u increases, it will exponentially decrease. So this is density of states. This is Boltzmann factor. This is Boltzmann factor. Okay. Now I will take the product of those two. I will take the product of e by u raised to 14 and e raised to minus 15 into e by u minus 1. Okay. This is the graph. On the x-axis, I will denote it as e by u. Okay. Then this yellow curve is the Boltzmann factor. This white curve is the density of states. The product of these two functions will give you this green curve, and you can clearly see that the maximum of green curve, that is this E star, that is I denoted it with the red line, okay, that is not equal to the mean value of energy U. Mean value of energy U. There is a small deviation. There is a small deviation. Okay. Now, what happens if you take n is equal to 1000? What happens if you take n equal to 1000? Then the exponential factor becomes e raised to minus 1500 instead of 10. When it is 10, here it is e raised to minus 15. When it is 1000, it becomes e raised to minus 1500. E by u minus 1. The graph is this red one. This is not red, it is green one. This is a rapidly decaying function. Then what about e by u raised to 3n by 2 minus 1? 3n by 2 minus 1 is here 1499, and that plot is this white graph. Again the product that is represented here as the yellow curve. Now it is almost symmetric. Now it is almost symmetric, the graph. So as n increases and in the limit n tends to infinity, this will be exactly symmetric and E star will be exactly equal to U. The limit n tends to infinity. For n equal to 1000 itself, it is almost equal. E star is approximately equal to U and the curve is almost symmetric. And another important factor is here, look at the width. Look at the width. It is from 0.90 to 1. Say 1. 0.90 to 1.1. Only 0.2. The width is 0.2. What about this graph width? It is from almost say zero point 0.4 to say 1.8. So the width of the graph is very large here. As n increases, this width will decrease. Here you have to look at the axis. Even though both the graph looks like same, the width looks like same, but the graph, the points are different. Here this one width is zero point 0.5, but here this one width is 0.05. Okay, so width of the graph decreases as n increases. In the limit n tends to infinity, this will be like a Dirac delta function. That means the fluctuation in energy or the spread of energy is very small. Even though the canonical ensemble, the systems in canonical ensemble can take any value from 0 to infinity theoretically, the practical case is like this. It will take a small range of energy around the mean value. All the other have very or negligible probability. The significant probability having only for this range of energy, and that depends on the value of n. As n increases, that range decreases. That is why microcanonical ensemble and canonical ensemble gives you identical results. Now the last point is we will calculate the partition function Qn of Vt. Partition function is integral 0 to infinity e raised to minus beta e g of e dE. This is the definition we studied in lecture number 9. Then g of e raised to minus beta e becomes, this is our definition we derived in this lecture, this expression, and substitute here. Then this term is constant, e raised to minus beta u minus ts is constant, take it outside. Integral 0 to infinity e raised to minus e minus u the whole square divided by 2k t square cv dt. E raised to minus beta u minus ts, integral minus infinity to infinity, e raised to minus y square dy, square root 2k t square cv. Why? I substituted e minus u by root 2k t square cv as y, then dy is de by root 2k t square cv. So substitute for de from here. Why I changed the limit from 0 to infinity to minus infinity to infinity? Here we are going to integrate over this line, and this function has value only in this range. So if you are taking 0 to infinity or from minus infinity to infinity, it will not make any difference. Okay, because the contribution only comes from a value which is greater than 0. So you can add minus infinity to 0 to this integral. It doesn't make any difference. But we know that minus infinity to infinity e raised to minus y square dy is root pi. Root pi. So that value will give you square root 2 pi kt square cv. So logarithm of this quantity, if you take logarithm of this quantity, it will be minus beta u minus ts. This exponential will go. And here log of 2 pi kt square cv raised to half. Now take minus kt log q, then this minus beta will cancel and you will get it as u minus ts minus half kt log 2 pi kt square cv. This first term u is proportional to n, entropy is proportional to n. So that means u and ts, both these terms proportional to n. What about this term? K constant, t constant. Logarithm of cv is proportional to n. So this term, last term goes like log n. First two terms goes like n. So compared to n, log n will be very small. If n is 10 raised to 23, log n will be 23, only 23. So you can neglect the last term compared to the first two terms. And you can write it as minus kt log q, that is nothing but Helmholtz free energy. It is approximately u minus ts. So all the results are consistent with our previous results. This is a well-known result in thermodynamics. Helmholtz free energy A equal to U minus Ts. Even though we consider here S, this X entropy, this entropy is actually comes from our definition of microcanonical ensemble. Okay, we introduced S from here, here. So this comes from the concept of microcanonical ensemble. Okay, but this A comes from the partition function, that is a canonical ensemble concept. So we can treat in the same equation itself, some quantities you can take from microcanonical ensemble approach, some quantities you can take from canonical ensemble approach. The final results are consistent with the experimentally observed values or already existing results. Okay, so that is why we can use canonical ensemble or microcanonical ensemble to derive the thermodynamics of the system. Theoretically, canonical ensemble can take any value of energy between 0 and infinity, but practically, the energy will spread only over a very small range with a significant probability. That is, it is identical with the microcanonical ensemble. Okay, thank you.